Yeah, so this is Christian Canham. It's retrograde rocket landing simulation. We'll get right into it here. So let's go and start off with a little bit of background. So your traditional multi-stage rocket, how's it work? It goes up, and then the second stage separates, and the second stage continues on into orbit. And then what typically happens, first stage simply just burns up in the atmosphere or it tumbles down and lands in the ocean, something like that. So that's not the case if you want to reuse that first stage. Um, so what happens there is right at stage separation as modeled in this image on the right here, the first stage has to kind of flip around and do kind of a 180 so the engines are facing the reverse direction. Then it does what's called like a boost back burn to slow down its horizontal speed. And then it does what's called like a re-entry burn to slow down vertical speed during re-entry to minimize heating. And then lastly, it does its landing burn to ideally land back on Earth at elevation 0. It's supposed to be at velocity 0. So that's the idea. So this is all enabled by some key additions onto that first stage. Namely, you have these what's called like reaction control thrusters that enables the rocket to tilt around when you're in the upper atmosphere. And you have grid fins that enable the rocket to maneuver once you're in the atmosphere. So in this simulation, in this presentation, it's essentially starting right at apogee, right after this stage flips around. So everything's from 2 and on. All right, I'll get into the little model setup here. So as I mentioned, landing simulation, it starts at second stage separation at altitude apogee, right after that first stage flips around. There are a few key simplifications that really aided in this model creation. The first one is the flight path is modeled in this 2D, two-dimensional plane down here. It's the X plane. And that is justified by the fact that, in this one key example, real life example that SpaceX has of reusing their rocket, they essentially have like a linear path from launch to stage separation to landing. So it's essentially linear there. So it's kind of a 2D plane. Second simplification is the curvature of the Earth is not modeled. That's somewhat justified by the fact that my velocities, they are not at orbiting velocity yet. They're about a little over half orbital velocity. So now we'll get into initial condition setup. So we turn your attention over to this chart on the right here. And this is showing actual telemetry data from a SpaceX rocket launch. So on the left in red, that's kind of the launch phase. And on the right in green, that's the landing phase that our team's trying to model basically. So in this orange curve here, this is velocity, blue is position or altitude. So to get this initial conditions for the simulation, I'm basically looking at stage separation, which happens at altitude apogee, or at velocity, the minimum right here. And I'm basically assuming that all the velocity at this point is in the horizontal direction. So this is kind of the initial stage, initial conditions, what it would look like. You have this first stage that's perfectly flat, and all the velocity is pointing as an arrow off to the right at 293 meters per second. I'm calling this basically negative 90 degrees. It's flat. So let's go on to the top level Modelica model. So this is split up into the physical model and the flight computer. So for the physical model, you have this multi-body cylinder. And again, this is kind of based off of the SpaceX Falcon 9 rocket, which is really the only true working example of this seen in real life. So that's 48 meters long, 3.7 meter diameter, and it has a density of about 0.3 grams per centimeter cubed. And that density decreases over time based on the fuel consumption, which is the second bullet point here. So fuel consumption, that's modeled with over here in the far right, in the lower right here, fuel injector. And that's basically consuming both fuel and oxidizer in this 1-to-2 volumetric ratio. So over time, the mass of the rocket or the density that would decrease. Then drag is modeled here in the very bottom, and that's just with a force vector normal to the center of gravity. And that drag is calculated based on the first stage's altitude at any given time, as well as its um, rotation relative to its path of motion. So if the whole flat side of the rocket is exposed versus just the end, that would affect, of course, the drag. And then last, we have control of this physical model, and that's done with these 3 grid fins on top you see, and these engines off to the left. And the second aspect of this model, as I mentioned, is the flight computer on the right here. And that is split into basically these different flight mode specific functions. So for example, I was talking about those entry burns and those landing burns. So you have like a different function for each of those different aspects. And inputs, you have the flight computer clock and your inertial measurement unit, which is giving you basically velocity, position, acceleration, all that good stuff. Output, have grid fins, engine thrust, and the gimbal angle of the engines. So now I'll get into just a little bit more detail these actuators. So start with the engines. This is the flight computer basically selects the gimbal angle of these engines, and it can be essentially plus or minus 10 degrees from a normal vector originating from the base of the rocket, pointing straight out. So that kind of mimics these Merlin engines that SpaceX has that are able to gimbal around a little bit, but are essentially locked in place. And then basically have a max thrust that is produced from these engines of 2,700 kilonewtons, and that is based on the fact that SpaceX uses a maximum of 3 of these Merlin engines for landing, and each of those Merlin engines has a max thrust of 900 kilonewtons. Then we'll get into the grid fins down here. So there's 3 grid fins. They're spaced 120 degrees apart on the upper stage, and they basically impart torque on the body of the first stage. The grid fin effectiveness at it being able to impart the torque is based on the rocket's velocity. So if it's traveling faster, it's able to impart more of a torque. If it's just standing still, like at landing, then it's not effective at all. Altitude, of course, because upper atmosphere have very little atmosphere to impart this torque. Control surfaces are essentially not effective at all. And then the fin angle, so that's modeled in the sine wave right here. So past 45 degrees, it's just essentially being modeled as drag as opposed to actually imparting the torque. And then mention that this first stage model, it's operating in the 2-dimensional plane. So essentially 2 of these grid fins are just keeping it in that 2D plane. Well, the third one is really the only one that's doing much. The 2 are just they're keeping the plane to for inconsistencies in the simulation. So give an overview of this flight computer. So inputs we have in green here. So you have your IMU inputs and your angle inputs. Outputs are listed in purple here. So you have your grid fin controller and your outputs to your engine over on the far right. In kind of yellowish orange here on the far left. These are kind of the 3 different function controllers that I was referring to earlier. So one for each of the burns, the landing burn, the boost back burn, and the entry burn. So basically a simple 30-second burn for the entry burn that's triggered by the altitude of the first stage. Boost back burn, that's looking at the horizontal velocity that gets below a certain point, then that shuts off. landing burn. That's just a little PD variant controller that's basically decreasing velocity and altitude, ideally to zero proportionally until it reaches sea level, essentially. So I'll go into a little bit. We also have this grid fin controller here in the top right. So I'll go into a little bit of that right now. So grid fin controller, it's split into basically a small and large signal controllers. So the small signal controller, it maintains the first stage's orientation, normal to the velocity vector. So essentially, when this first stage is falling through the atmosphere, if you don't have this small signal controller, it would just tumble end over end out of control. So this keeps that first stage upright, pointed, essentially downrange, engines down. Then we have this large signal controller, which basically is responsible for orienting the rocket from this horizontal starting position to vertical. And it also guides the first stage toward the landing zone. So here in the right, you can see the large signal controller. So I have this little ramp function. That's what's bringing it up from horizontal to vertical. And then this location controller. And that's where this PD controller is that guides the rocket to the landing zone. At the bottom here, we have angle plotted on the y-axis and radians and time on the x-axis. And this is basically looking at the effectiveness of the grid fin at orienting the rocket. So in red, you have the grid fin angle. In green, you have the desired orientation of the rocket. Blue, you have the actual orientation of the rocket. So see, it's kind of repositioning the rocket, a little bit underdamped, as you can see here, but overall effective. And then we'll move into the final landing simulation. So we had the simulation, but it required heavily tuning a lot of the different controllers, a lot of like the timing in order to actually land it. So if the simulation was successful, if it successfully landed it, it's basically shown in green here. If it's unsuccessful, it's red. So what's a successful landing? That's if the first stage lands within this 550 meter predetermined landing pad right here at, what is that, 10 kilometers. And then we have, basically has to not be speeding towards the ground. So determine, less than 2 meters per second velocity at ground. Fuel reserves also could not be depleted. Otherwise, you basically consider that your engines could not burn and the rocket was not effective at that point. So over here on the right, this is basically a plot of altitude plot on the y-axis and horizontal velocity on the ground in your x-axis. It's basically showing that you have slightly different initial conditions at the top, and the controllers are basically able to correct for that a little bit. At a certain point, though, controllers can't land the rocket, even if it's like if the starting velocity is too low. For example, it's not, the controllers don't have enough control authority to bring it all the way over to the landing pad. So things like that we were tinkering with. So next, I'll go into the comparison to actual SpaceX telemetry data. So this is publicly available data that you might see from one of their launch broadcasts that they put up on the screen. So someone compiled this into kind of a CSV file where you can just essentially plot it and against what the simulation is doing. So the simulation is in blue and the SpaceX telemetry data, that's red. So it fairly closely models it in these boxes. You can see the different burns that are occurring. This boost back burn, upright maneuver, entry burn, that's what's really slowing it down. So you can see the curve flattens out a little bit there, and then lastly the landing burn. So I would note though that when making this model, we did reference this data. So we kind of tweaked it a little bit so it fitted this. We didn't just complete this and then look at this and oh, it works. But yeah, we did reference this as we were building it. And then lastly, I'll go into some of the visualization that we worked on. So there's this basically DLR visualization library that offers a method to create these basically immersive animations that you can do. So we did this because, you see those 2D plots and it's kind of difficult, I guess, for others that are not familiar as much with the work to understand what's going on. And that's where this visualization library comes in. It offers a very like compelling way to see what's going on. If you really wanted to, you could put on like a VR headset and be immersed fully in this environment. So in this image on the right, you can see our simulation. So down below, you can see kind of Cape Canaveral, Florida, with the landing pad in the bottom there, and then that first stage coming down, the grid fins right on the top there, and then we have the plume of the engine exhaust. You can like tweak all these different visualization bodies. Like for example, the engine plume, the upper atmosphere, you can control, made like the width wider to account for the decreased pressure in the upper atmosphere. It gets narrower as it goes down towards sea level. So in conclusion, we have this simulation demonstrates basic control fundamentals in recovering a rocket first stage landing vertically back on Earth. So it's a relatively good approximation of the SpaceX Falcon 9 first stage, which we were trying to mimic here. But that being said, it does have some key simplifications that make the model building a lot easier. And with that, that is all I had, and I will take any questions if anyone has them.